Okay, so this is part 3 and last part of lecture 7, and we are going to conclude the proof of Heron's proof or Heron's formula. This is part C of it. We are going to incorporate parts A and B from the previous part 2 of the lecture. So here I have drawn the picture once again, and basically what we proved from the other part. We proved that this is length S minus C, S minus A, S minus B. We also proved that this angle and this angle are equal, this angle and this angle are equal, and these two angles are equal. So I marked them. I'm calling these two angles beta, these two angles alpha, and these two angles gamma. Alright, so far that's what we had from before. Now I'm going to begin again with the triangle ABC, and we are going to add few extensions. So add few extensions. What are the extensions? Few extensions. Alright, so the first thing we do, I am going to draw a perpendicular with the line OB. By the way, the center here, I don't want to make the figure heavier than it is with notation, but the center of the circle is what I'm calling O. So this is the line OB, and I'm going to draw a perpendicular line with it. So I'm going to draw a perpendicular line with it. So here it is. Okay, so that means that this angle is right. So the first thing I do is the following. I'm going to draw, draw the line OL perpendicular to OB. So this is the line OL, and it is perpendicular to OB. And also line AM perpendicular to line AB. That means I'm going to draw the line AM perpendicular to line, okay, so this is the line AM. It is perpendicular to AB, and they intersect at some point. Let me call it point K. The perpendiculars intersect at K. So this is point K. Okay, and also I'm marking on AB this point H as well. Mark also OH, and connect B with K. Okay, and connect B with K. So I'm going to connect B with K. Okay, B with K. Now, consider the following quadrilateral. So consider AOBK. AOBK. Consider AOBK. Okay. By proposition 4, that we mentioned and proved before, proposition 4 from preliminaries, what we will have? We will have a circle. So a circle can pass through these 4 vertices. Okay, a circle can be drawn, can be drawn passing through these 4 points, 4 vertices, passing through vertices A, O, B, and K. Okay, what does that mean? And then by proposition 5 and by proposition 5, refer to your previous pages. We have what? Angle AOB, angle AO, this is the center, AOB, plus the angle AKB, being the opposite angles in this quadrilateral, their sum is 2 right angles. That is by proposition 5. So we will have angle AOB plus the angle AKB, so AOB plus AKB, they are opposite angles in this quadrilateral, and their sum is 180, or 2 right angles. So angle AKB, it is equal to 2 right angles. I'm not going to write entirely right angle, but just RAs, and that stands for right angles. Okay, now by congruences of part B, in part B we proved or we showed that we have 3 pairs of congruent triangles. So by those congruences of part B we have the following. So by congruences of part B, we showed that this triangle is congruent to this is congruent to this, and this is congruent to this. It'll follow that these 2 angles, so 2 gamma plus 2 beta plus 2 alpha, would be equal to 4 right angles, or 360 rather. So by congruences of part B, we have 2 alpha, this angle plus this angle, plus 2 beta, this angle plus this angle, 2 beta, plus 2 gamma, gamma plus gamma. It will be equal to 4 right angles. Okay, that would mean that, so this would imply that just the angle alpha plus the angle beta plus the angle gamma in themselves as a sum, it is equal to 2 right angles. If you factor out the 2 and divide by 4 by 2, that's what it comes to. And this is the same as saying as angle alpha plus beta plus gamma is the same as angle AOB. So beta plus gamma is the same as angle AOB. So instead of writing beta plus gamma, I'm going to write angle AOB. It's the same angle. We're saying that gamma plus angle AOB is also equal to 2 right angles. But what do I know? I know that AKB, this is a right angle, angle AKB, plus the angle AOB, again from proposition 5, plus the angle AOB, the same angle, is also equal to 2 right angles. So if we subtract from equals, the leftovers will be also equal. This is by one of those common notions, if you remember, that we talked about. So this would mean that angle AKB is equal to the angle alpha, or alpha is equal to angle AKB. Okay. Next we consider, we consider another pair. we are going to consider triangle COF. Oops, this is F, not E. So COF, triangle COF, and triangle ABK, and triangle ABK, ABK. Okay, so COF, this little triangle and this other large triangle, ABK, this bigger triangle. So this small one, I don't know if I should actually mark it, but so let me just make it with red lines, so you know what triangles I'm talking about. This triangle with this FOC or COF. Okay, these two right triangles. Alright, I'm going to consider both of these triangles. Now, what can I say about angle CFC? CFC or KAB? Not CFC, but OFC. OFC, angle OFC is equal to angle KAB, as they both are right angles. It's equal to the angle KAB, and they both are equal to right angle. Okay. Also, angle FOC, angle FOC is equal to what angle? FOC is angle alpha, and I just proved in the step before, that this angle is equal to AKB, is equal to angle AKB from this step here. Angle FOC, I'm calling that angle alpha. Okay, that we know from the step before. So this means that these two triangles are what? They are similar to one another. So triangle COF is similar to triangle ABK. Similar to, and I'm going to triangle ABK, and I'm going to use some properties of similar triangles to deduce the following. And we have the following. By similarity of these triangles. So ratios of some sides are equal to one another. So AB over AK, so AB over AK is the same as FC to FO. Is the same as FC to FO, and they are also the same as AG, well, because FC is equal to CE and CE is equal to AG by construction. That is in part A of the proof. So instead of AC, I'm going to write AG. And what is FO? FO is the radius of the circle. So, okay. So since FC is equal to CE is equal to AG from part A. All right. So this means from here I can deduce that AB over AK is equal to, I'm sorry, AB over AG. If you cross multiply and divide, you'll have AB over AG. That would be equal to AK over R. So let me box this equality, and I'm going to call that 1. Because I'm going to do something similar with another pair of similar triangles. So similarly, I'm going to consider 2 other triangles. Triangle AKH, triangle AKH, with triangle HOD, HOD. So let me try to do them green now. That's probably too much, but I hope not anyway. So now I'm considering the green ones. Should probably make the lines and this green one with this other green one. Hopefully it makes a difference in notation, so it's not as heavy in notation. Okay, so similarly, AKH, the green one, is similar to HOD, is similar to triangle HOD, and that is because angle KAB, KAB is a right angle, and also HOD, I'm sorry, HOD, I should say HOB, not D, are equal to right angles by construction. Okay, and angle AHK, let's see, AHK is equal to angle OHD, because they are vertical angles. So angle OHD, this was proved before in Elements, one of the first books of the Elements, that vertical angles are equal. They are vertical. They are vertical angles. All right. So that's why they are similar. Hence we have the following relations. We're going to have now AK over AH, AK over AH, this is the big green triangle. It is equal to OD over HD in the small green triangle, OD over HD in the small triangle. Well, OD is equal to R because it's the radius. OD is the radius of the circle, and we call that R, and leave that over HD. Okay, so that implies if you do some cross multiplying and dividing again, you have AK over R would be equal to AH over HD, which further again would imply the following, would imply that AK is equal to, let's see, what is AK? So AB over AG, I'm sorry, is equal to AH over HD. Okay. I'm going to box that again, and I'm going to call that part 2. And yet another third pair of similar triangles would be the following. So I shall say similarly, I'll continue here. Triangle OHD, I'm just going to point to it. I'm not going to add more colors, as that would be terrible. So triangle OHD, this little green triangle, is similar to triangle ODB, to the triangle adjacent to it. Triangle ODB. I wonder if I can add green, but I won't. And that is by proposition 3. If you look at the proposition 3, stated before, by proposition 3. All right, so and we have, since these two are also similar triangles, we will have the following relation: HD over OD, so not HD, HD over OD, sides of this right triangle, are their ratio, this is OD, I'm sorry, their ratio is equal to OD over DB, But this would mean that HD times DB would be equal to what? Would be equal to R squared. Now, what we're going to do is we are going to add equation 1 to both sides of equation 2. Not equation, but there's two equalities. So we are going to add equality 1. I'm sorry, not equality 1. We are going to add 1 to both sides of equality 2 that I have boxed here. So add 1 to both sides of equality number 2. Equality number 2 is this, and I'm going to add 1 to both sides. So I will have AB over AG plus 1 is equal to AH over HD plus 1. Okay, and if we put things on the same denominator and do some algebra, this is the same as saying AB plus AG over AG. It is equal to AH plus HD over HD. Okay. So this would imply that BG, well, AB plus AG is the long one, BG. We will have BG over AG, AH plus AH plus HD. This is the same as AD over HD. Okay. So both sides, I'm going to multiply by 1 both sides of this equality, but you can change 1 to something convenient. For example, BG over AG, you can say times 1, or instead of times 1, you can say times BG over BG. Okay, and here AD over HD, you can multiply that by 1, or the same as multiplying by BD over BD. Okay, so from here we'll have what? We'll have BG squared over AG times BG over AG times BG equals to AD times BD over, well, HD and not BC here, but BG, sorry. That would be equal to R squared. I'm going to box this, and I'm going to call that the third equality. In this third equality, cross multiply. So we are going to cross multiply here, and I will continue here. If you cross multiply, we have what? We have BG squared times R squared is equal to AD times BD times AG times BG. AD times BD times AG times BG. Okay, well, what is BG squared? We said in the very beginning, part A, we proved that BG is nothing other than the length S, which is the semi-perimeter of the triangle. So here we'll have S squared times R squared. AD we proved from before to be what? To be S minus A. This is your AD. Yeah, this side AD is S minus A. BD, where do I have? BD we proved to be S minus B. AG we proved to be S minus C. And BG is nothing but S. We proved that. So from here we have that S times R itself is the square root of this quantity. So S times S minus A times S minus B times S minus C. But what did we say SR is? SR, in the very beginning of the proof, we proved that is nothing other than the area of the triangle in terms of S and in terms of R. So this is area of triangle ABC, and we're saying that it is equal to this quantity, and that would be the end of the proof. Now, I'm not going to do it, but it's worth mentioning that you can actually use Heron's formula to give yet another proof of Pythagorean theorem, but again, we are not going to explore that for this lecture. And this will be actually the end of lecture 7. So long until next time.